Last month, a headline detonated across tech. Google shrank 31 gigabytes of AI memory down to 4, and the number holds up. 10 million documents that used to eat that much RAM folded onto a box a quarter the size and searched faster than Meta's face while they did it. But look closer, because the thing it shrinks is not the model. It is the vector index. Every RAG app, every AI agent, every semantic search you have ever touched leans on one of these. It is how a machine finds things by meaning instead of by keyword. And at scale, that index quietly becomes one of the biggest lines on your cloud bill. The usual way to shrink it comes with a tax. You train a codebook on your own data first, which is slow, and it breaks the moment your data shifts. TurboQuant throws that step in the bin. It skips training, never once looks at your vectors, and still lands the same compression. That property has a name, Data-Oblivious. The output is byte for byte identical, whether it runs on your vectors or mine. Now the part the headlines missed. Google wrote the math, but never shipped the tool everyone keeps screenshotting. Which leaves two questions. Who actually built it? And how do you shrink something you never look at? If you run any kind of retrieval, this one lands on your wallet. Start with what a vector really is, because the whole trick lives there. When an AI reads a word, an image, or a full document, it turns that thing into a long list of numbers. One point floating in a space with hundreds of dimensions. Things that mean similar stuff land near each other, so search stops being about matching letters and becomes about matching meaning. The problem is weight. One embedding from a modern model can run past 1,500 numbers long, and each number is a 32-bit float, 4 bytes apiece. So a single vector weighs around 6 kilobytes before you have stored a word of text. Line up 10 million of them, an ordinary size for a company knowledge base, and you are holding roughly 31 gigabytes of raw floating point in memory all day. That is the map every query walks across, and it never gets to rest. Older compression does shrink each number, but it plays a sneaky game. To rebuild the values later, it stores a full precision constant for every little block of data, which adds a bit or two back to every number, so the budget you are protecting leaks right out. The fancier method, Product Quantization, learns a codebook by running k-means over your vectors first. It works, but it means a full training pass before you can index anything, and you rerun it every time your data drifts. That is friction, and friction is what kills adoption. Here's where TurboQuant does something that feels like cheating. Strip the length off each vector, and what is left is pure direction, a point on the surface of a giant high-dimensional sphere. And directions have a hidden statistical habit you can exploit once you set them up right. So it sets them up by spinning them. Every vector gets multiplied by the same random rotation matrix. One shared spin for the entire data set. After that rotation, each coordinate independently follows a known bell curve, no matter what the original data looked like. Random text, product photos, medical records. It does not matter. That single fact is the whole unlock. Because the shape of every coordinate is now predictable, you can work out the best way to round it ahead of time, straight from the math, without peeking at one real vector. The data never teaches the compressor anything. The geometry already did. Concretely, you pick how many bits you can spend. 2 bits gives you 4 buckets to sort each number into. 4 bits gives you 16. The boundaries come from a classic technique called Lloyd-Max, computed once from theory and reused for every data set on Earth. Then you bitpack the results as tight as they go. A1 500 dimension vector that used to sit at 6 kilobytes now fits in 384 bytes. That is 16 to 1, and because the rounding was optimal, the results barely move. Google stacks 2 ideas together. The first, rotate and round, spends most of the bits capturing the core of each vector. The second is a 1-bit sign trick called QJL that spends a single leftover bit cleaning up the error at basically 0 cost. Add them together, and the distortion lands within about 2.7 times of the Shannon limit, the hard floor for how little information you can throw away at a given size. There is almost no better compression physically possible. So who actually built the thing in the headline? Google published TurboQuant as a research paper, accepted to one of the big machine learning conferences, and left it there as math. Then an independent developer named Ryan Coadry read the paper and turned it into software you can install. He called it TurboVec, wrote it in Rust with clean Python bindings on top. The headline feature is online ingest. You add vectors, and they get indexed on the spot. No separate training step, no rebuilding the index as your collection grows. It drops straight into tools like LangChain and Llama Index. And his benchmark is the exact clip that went viral. That same 10 million vector index, bloated to 31 gigabytes as raw floats, now rides in roughly 4 and answers queries faster than FAISS while it does. That speed is not luck. Coadry hand-wrote the search kernels in the chip's own SIMD instructions, one built for ARM and one for Intel. And on ARM, they beat Meta's heavily tuned FAISS fast scan by 10 to 19%. It also filters inside the search, not after it. Hand the query a list of allowed IDs from a permission check, and the kernel only scores those candidates. So hybrid search stays exact and selective filters run faster instead of slower. The whole thing runs on hardware you already own. No managed service, no data leaving your walls. That is the difference between a demo and something a hospital or a bank will deploy for private, air-gapped retrieval. And Google's own reason for building this is bigger than search. The same rotation math squeezes the KV cache, the scratch memory a model fills while it reads a long conversation, and it is why 100,000 token chats get so expensive. TurboQuant cuts it by around 6 times, down to 3 bits, with almost no drop in answer quality. On a top data center GPU, the 4-bit version computes attention up to 8 times quicker than uncompressed keys, so the cost on long context work roughly halves. You fit about 6 times as many long chats onto the same GPU. If you rent those cards by the hour, that is the invoice getting shorter. Wall Street felt it right away. Memory chip makers took a hit, Micron and Western Digital both sliding a few percent in a single session, and traders started calling it Google's DeepSeek moment. The fear is simple. Cheaper AI memory means fewer memory chips sold. That panic is probably backwards, and history agrees. Every time memory gets dramatically cheaper, we do not buy less of it. We find 10 new uses and buy more. It is an old idea called Jevons paradox, and it is already leaving the lab. The rotation trick now ships inside Qdrant, one of the most popular vector databases, so developers get it as a checkbox. To be fair, one caveat before you tear out your stack. What Google released is a paper and an algorithm, not a supported product with a phone number to call. Hardening the production-grade tooling is still on the open source community. The math is shipping. The polished download button is not yet. And that is what makes this useful, not just clever. The win is not the compression ratio. It is the absence of friction. With no training run and no codebook to babysit, you can bolt it onto a system you are already running this afternoon. So here is the honest read for your own stack. Under a few 100,000 vectors, what you have is fine. The moment you cross into millions of vectors, or you are paying for long context serving by the hour, this is the first lever to pull. It costs nothing to try, and it does not touch your accuracy in any way you will notice. One shared random spin turned the problem from compress my data into compress anybody's data. And that is how 31 gigabytes of AI memory politely folded down into 4. If watching a giant model shrink into a tiny footprint is your thing, the next one is wilder. A 700 billion parameter model running on a laptop with no GPU at all. Same instinct. Squeeze the memory and push to the edge. That link is on screen, and I will see you in the next one.